The moment I saw the preliminary trajectory of the object designated 3I/ATLAS, I realized something had gone terribly wrong in our understanding of interstellar visitors. The data didn't whisper uncertainty, it screamed disruption. A third confirmed interstellar object had slipped into our solar system, and within hours the JPL orbital solution made one fact unavoidable. This thing was not behaving like a typical comet, nor even like an erratic piece of debris. Its path was hyperbolic, yes, an unmistakable signature of an origin outside our sun's domain, but its luminosity curve flickered in a way that betrayed structural instability. It was already shedding pieces, as though it had been mauled by some massive force long before we found it. When the fragmentation pattern stabilized, the largest remnant, 3I/ATLASA, emerged as the real threat. The shift in its orbit was subtle, the kind of deviation that would slip past casual observers, but I've learned over the years that cosmic catastrophe often hides behind small numbers. A slight pressure from solar radiation, an asymmetric release of volatile gas from a crack created during its interstellar journey. Whatever the cause, the effect was brutally clear. The fragment was now on a direct collision course with Venus. Not in decades, not in years, in weeks. I remember staring at the updated Venus impact probability map, a violent red splash dominating the chart, and feeling something I rarely feel in astrophysics: urgency. Planetary motion is usually stately, elegant, indulgent of human timescales. But not this. This was a bullet fired across light years, aimed carelessly, yet now barreling toward a world whose atmosphere is thick enough to crush steel and hot enough to melt lead. And we were about to witness what happens when a piece of interstellar matter traveling at over 50 kilometers per second meets a planetary furnace. The tension escalated fast once Hubble locked onto the object. The brightness spike confirmed its size, easily comparable to a large asteroid, though inconsistent in density, as if its interior were a patchwork of ancient materials stitched together by time and cosmic radiation. Its speed made interception impossible. Even if we'd launched a probe the second we detected it, the fragment would still outrun any hardware we could dream of deploying, so we did what humanity always does when powerless against scale. We observed, and we waited. The first pre-impact interaction arrived in the form of a bow shock captured by Akatsuki. Normally, shocks like this are subtle, measurable, not visible. But this one blazed with ionized debris, the raw breath of an object slamming into Venus's gravitational sphere at interstellar velocity. Even the telemetry felt strained, as though the spacecraft itself were flinching, and then, almost without warning, the fragment crossed the final threshold. An object moving that fast does not enter an atmosphere. It tears its way in. The air becomes a weapon, the pressure a sledgehammer, the heat a starburst of violent dissociation. 3I/ATLAS-A didn't burn up. It exploded into a sustained aerodynamic blast that carved a luminous wound across Venus's sky. I watched the live spectroscopic feed from Mauna Kea, a rising column of plasma, white at the core, bleeding into violent blues and greens as unfamiliar compounds vaporized. For a brief moment, the object's death shone brighter than any volcano or lightning storm Venus had produced in recorded history. But the real shock came after. Venus's atmosphere didn't simply absorb the impact, it buckled. A temporary gap tore open in the upper cloud layer, like a wound held apart by invisible hands. Gas surged outward, not escaping easily, but escaping nonetheless. I could almost feel the collective breath of every researcher watching the same feed. This wasn't just another interstellar object. This was a messenger from a system we had never touched, delivering its last message by dying in the skies of a hellish world, and in doing so, altering that world's atmosphere in ways we had never predicted, never modeled, and certainly never prepared for. The moment the atmospheric wound on Venus began to close, I realized we were witnessing the end of the fragment's physical existence, but the beginning of its scientific afterlife. The sensors continued to register turbulence long after the plasma column faded, a kind of atmospheric ringing, as though the planet itself were vibrating from the shock of having its skies torn open. But the final descent of 3I/ATLASA was only the climax. Its death had left fingerprints across the entire approach trajectory, and those too demanded explanation. Hubble's enhanced imaging showed the fragment's earlier shedding had not been random. There was a rhythm to the debris trail, a pulsing as if the structural stresses were oscillating under the competing forces of solar heating and internal fractures. Watching the time-lapse, I felt an eerie sense of anatomy, like I was looking at the bones of something that had lived a long time in the dark between stars and was now collapsing under the sudden violence of a stellar neighborhood not its own. Yet the closer it came to Venus, the more violently it behaved. The bow shock we recorded was so intense that it distorted the ionosphere ahead of the impact point, producing a ripple that behaved almost like a gravitational lensing effect. The energy involved defied the simplicity of cometary physics. As the fragment plunged deeper, its velocity wasn't just destructive, it was revelatory. The shock front tore open pockets of gas within its structure, releasing compounds that fluoresced under solar radiation. For a few fleeting minutes, 3IATLAS-A looked like a dying star, shedding layers, each one giving us a spectral signature older than any rock we'd ever touched. And then came the final incineration event, a roar of frictional heat, followed by a burst of ionized debris that scattered across the super-rotating winds of Venus. But the true violence happened out of view. The fragment was too large, too fast, and too structurally unstable to create a single crater. Instead, it forced its way through the dense Venusian air like a drill bit of vaporizing stone and metal, causing an aerodynamic explosion so prolonged that the upper atmosphere peeled apart. It was as if someone had ripped open a curtain that had hung undisturbed for billions of years. The physics of it were brutal. The upper cloud deck, made of sulfuric acid droplets, was vaporized into a shock plume that reached hundreds of kilometers above the surface. The pressure differential created a temporary escape channel, a crack through which lighter gases streamed outward. From Earth, the event looked like a shimmering spike of light piercing Venus's cloud tops, but the real insights came from the post-impact data. Venus's atmosphere did not behave as a passive medium. It reacted, it fought back, it absorbed, expelled, recompressed, and rang like a bell. The fragment's death triggered what I can only describe as a gravitational bleed. The explosive decompression allowed hydrogen and oxygen, normally trapped deep within the atmosphere, to be blasted beyond the escape velocity threshold. I watched the numbers come in, mass loss far higher than any simulation predicted. It was a planetary exhalation forced by an interstellar punch. But even more unsettling were the chemical anomalies. The vaporized remains of 3I/ATLAS left streaks of rare isotopes and organic compounds drifting in the upper haze. These signatures were not terrestrial. They were not Venusian. Their ratios of thorium to uranium, their distribution of carbon chains, it all pointed to a system that had formed under conditions unlike any we had catalogued. And that meant one thing. We had just received an unsolicited sample from a nearby stellar nursery, carried at unimaginable speed, preserved through interstellar cold, and delivered violently by cosmic accident. The scientific questions multiplied faster than we could answer them. How old was the object? What tore it apart before it reached us? What kind of star system could produce such material? And most unsettling of all, if a fragmented interstellar object could do this to Venus, what could a larger, intact one do to Earth? In the hours that followed the impact, what captivated me wasn't the explosion itself, but what Venus began to reveal as the atmospheric turbulence cleared. The so-called grand scar, as some of my colleagues began to call it, was unlike anything I had imagined. We expected a broad disturbance, maybe a glowing thermal plume or a localized shock signature. Instead, radar mapping showed a vertical column, a hollowed tunnel, extending through Venus's upper atmosphere. The fragment hadn't simply penetrated the clouds, it had torn a cylindrical void straight through them, a wound in the sky. From orbit, the scar didn't resemble a crater or even a burn mark. It looked more like an incision, long, distorted, stitched at the edges by swirling sulfuric acid clouds trying to reseal themselves. I ran atmospheric simulations, but none replicated the shape. To produce something like that, the object must have remained coherent far longer than expected, acting like a cosmic spear before vaporizing. Even more remarkable was the persistent thinning of the atmosphere around the scar. Venus's superrotation usually erases disturbances within hours, but this void fought against it. It refused to close. Then came the gravitational leakage. At first I thought the data was faulty, some calibration issue with the spectrometers on Akatsuki or the orbital probes, but as the hours passed, the measurements became undeniable. Venus was losing mass. Not large amounts, not catastrophic, but measurable. Hydrogen and oxygen, normally trapped beneath the crushing weight of Venus's lower atmosphere, were escaping through the wound left by 3IATLAS. It reminded me of watching water leak from a pressurized tank that had been punctured. The gas didn't gush out but seeped with a stubborn persistence. I realized with a chill that we were witnessing a natural experiment that could never be performed intentionally. A brief window into what happens when one of the most extreme atmospheres in the solar system is forcibly breached by an object traveling faster than any spacecraft ever built. And the leak wasn't uniform, it pulsed. The planet's rotation twisted the opening, letting bursts of gas escape rhythmically like a heartbeat. It was as though Venus, for the first time in billions of years, was breathing outward. But the most startling results came from the chemical signatures in the plume that drifted above the scar. When the interstellar fragment vaporized, it didn't simply mix into the Venusian atmosphere, it chemically collided with it. High-energy reactions forged compounds never before seen in situ. Isotopic readings revealed ratios that defied solar system formation models. The materials were older, colder, stranger, and embedded in the spectral lines were carbon-based molecules, long chains, complex scaffolds, not biological, but undeniably pre-biotic, the building blocks. I stared at the sequences. They were the kinds of molecules that, in the right environment, could seed chemistry leading to life. Venus, of course, was no cradle for such complexity, not anymore, but the presence of those molecules in an interstellar object forced a question I had spent much of my career contemplating. How many systems like ours were sending out their own chemical messages across the galaxy, tucked inside stray fragments cast loose by gravitational chaos? The scar on Venus offered an unexpected gift, the chance to analyze interstellar compounds that had survived eons of cosmic radiation, supernova debris fields, and cold interstellar clouds. Without the violent excavation caused by the impact, they might never have mixed with Venusian gases in a way detectable from orbit. The planet's extreme heat had acted like an analytical furnace, vaporizing, ionizing, and lifting the molecular remnants to altitudes where our instruments could catch them. Yet, as I studied the data, I couldn't ignore the deeper implication. The fragment brought with it a chemical fingerprint, an origin story carved in atomic ratios. The thorium and uranium content pointed to a system that formed in the aftermath of relatively recent stellar enrichment. A young star, metal-rich, possibly part of a cluster that had shed planetesimals during its chaotic youth. The fragment was a messenger from a place where the periodic table had played out differently, subtly, but enough to leave a signature. I felt an unfamiliar weight in my chest as I reviewed the isotopic distributions. It wasn't fear, it wasn't excitement, it was perspective. The impact on Venus wasn't merely a cosmological incident, it was a reminder that our solar system is not isolated. We are part of a vast, dynamic galactic ecosystem where material drifts, collides, and occasionally announces itself in a flash of fire upon a distant clouded world. The scar would eventually heal, the gases disperse, the chemical plume fade, but the message of 3I/ATLAS, its final act as it died in the Venusian sky, would echo much longer. In the days following the impact, as Venus's atmosphere slowly stabilized, the scientific community found itself confronted with a treasure we had never expected to receive, a natural accidental sample return mission from another star system. The vaporized remains of 3I/ATLAS, now dispersed across the upper haze of Venus, offered us something no spacecraft had ever brought back, unprocessed, unfiltered matter forged around a foreign sun. I remember the exact moment I saw the combined spectroscopic overlays from the fleet of space-based instruments. They reminded me of fingerprints smudged across a mirror, familiar in form, utterly alien in detail. The first surprise was the isotopic footprint. Venus's atmosphere has a very predictable chemical profile, sculpted by billions of years of extreme heat and volcanic activity. But threaded through the plume were atomic ratios that did not belong there, anomalies in thorium, uranium, and certain rare metals whose abundance patterns pointed toward a very different stellar nursery. The ratio suggested a star younger than our Sun, but enriched by more recent supernova ejecta. It felt almost like reading the genealogy of a stranger's family simply by examining the dust on their clothing. I spent hours comparing the readings with known stellar catalogs, searching for a system whose chemical evolution matched the pattern. None aligned perfectly, which wasn't surprising. Our maps of the galaxy are still crude. But the evidence was clear. The parent system of 3I/ATLAS was metal-rich, dynamic, and possibly part of a cluster that experienced intense gravitational scattering in its early history. The fragment may have wandered for millions of years, crossing interstellar caverns of cold and silence before stumbling into the gravitational pull of our Sun. But the real shock came from the organic signatures. Embedded within the vaporized remains were chains of amino acid-like structures, primitive but undeniably complex. Not life, not anything close, but the sort of raw molecular clay that, under the right conditions, could serve as a starting point. I felt a tension rising in the scientific community. Some rushed to proclaim evidence for panspermia, others cautioned restraint. But for me, the discovery did not need exaggeration. Its significance was already enormous. It showed that the raw ingredients of life are not localized luxuries of our solar system. They drift freely across the galaxy, hitchhiking on shattered worlds and wandering fragments. As I examined the spectral lines, I found myself thinking about the pathways such molecules might travel. A star system forms, planets collide, cometary bodies shatter, and debris is flung outward at escape velocities. A fraction of that debris, just a tiny sliver, might survive the violent ejection and wander for eons. And maybe, as in the case of 3I/ATLAS-A, one of those fragments eventually crosses paths with a planet like Venus and disintegrates in a blaze of light, leaving behind hints of what once existed light years away. It was a cosmic message in a bottle, shattered open by heat and pressure. Yet the chemical data told only part of the story. The structure of the fragment itself, the way it fractured, the materials embedded within it, the strange layering revealed during its vaporization, suggested a complex history. Some inclusions appeared to have formed in extreme temperature environments, while others bore the signatures of slow cold accretion. It was as though the object had lived multiple lives, born in fire, weathered in ice, then torn apart by gravitational chaos before reaching us. Each layer preserved a different chapter of its existence. As more high-resolution data came in, we discovered another anomaly. Some isotopic ratios were slightly skewed in ways that suggested exposure to unusually intense cosmic ray environments. Perhaps the fragment had traveled through dense regions of interstellar gas or near a past supernova remnant. Anything that could explain the presence of certain short-lived isotopes still detectable despite their natural decay. It was a reminder that interstellar space is not an empty void, but a dynamic landscape where matter is sculpted by time, radiation, and cataclysm. Yet what fascinated me most was not the chemistry or the isotopes, but the philosophical weight of what we were uncovering. The impact of 3I/ATLAS-A, violent, destructive, spectacular, had inadvertently given us the clearest evidence yet that we are part of a chemically connected galaxy. Material from distant suns rains into our solar system, collides with our worlds, mixes with our atmospheres. The seeds of complexity do not respect borders or star systems. They drift, they collide, they blend. And in the process, they remind us that our origins are not confined to a single place. We are participants in a cosmic exchange older than Earth itself. As I reviewed the data late one night, the thought struck me with quiet force. Perhaps the true message of 3I/ATLASA wasn't about destruction or spectacle, but about continuity. The fragment had died on Venus, but in doing so, it had given us a glimpse of its birthplace. Its atoms told us a story written before humanity existed, and it left us with a simple, profound truth. Interstellar objects are not visitors, they are messengers. And this one, through its fiery end, had finally been heard. In the weeks that followed the disintegration of 3I/ATLASA, the scientific world entered a state of uneasy clarity. We had witnessed something unprecedented, a fragment from another star system slamming into a planetary atmosphere at interstellar velocity, altering that world, leaking its chemistry into space, and leaving behind a set of clues that challenged everything we believed about how interstellar objects behave. But the most important consequence was not what happened to Venus, it was what the event revealed about us. Our defenses, our assumptions, our preparedness, our curiosity, all were suddenly laid bare. The first global meeting on planetary defense after the impact felt different from every conference I'd attended before. The tone wasn't speculative, it was sobered. Images of the Venusian scar hovered on screens as experts debated trajectories, detection thresholds, and the limitations of existing surveillance networks. We had focused for decades on asteroids and comets born within our own solar system, but 3I/ATLAS taught us that interstellar objects were not rare aberrations. They were messengers we had simply failed to notice. And one of them had just shown us that unlikely does not mean impossible. I watched as mission planners recalculated the requirements for tracking hypervelocity bodies from outside the solar system. The numbers were unforgiving. Objects like 3I/ATLAS-A approach fast, dimly, unexpectedly. They shimmer into existence only when they're already upon us. The idea of intercepting one after detection seemed almost absurd. We would need a network of rapid response telescopes, deep space sentinels stationed like guardians across the solar system, and automated probes ready to launch without debate or hesitation. For the first time, planetary defense wasn't about stopping an impact, it was about catching up to one. But the most radical shift came from the realization that studying interstellar objects required intercepting them before they passed by or collided with something else. The impact on Venus acted as a brutal, natural dissection, but we couldn't rely on planetary atmospheres to do our sampling for us. If we wanted to understand the chemistry of distant systems, their formation, their potential for life, we needed to reach the objects themselves while they were still intact. And for once, the scientific community unified around a single idea: dedicated interceptor missions. Plans crystallized quickly, probes that could be stored in standby mode, ready to burst into acceleration the moment a foreign visitor appeared. Ion drives, nuclear propulsion concepts, direct fusion ideas, technologies long relegated to theoretical papers suddenly felt urgent. The goal was simple: meet the next interstellar object before it leaves, collect samples, and bring them home. It was an ambition that once seemed fantastical, but after Venus, it felt overdue. Yet beneath the calculations and mission designs, a quieter realization was taking shape. 3I/ATLAS-A had shown us that interstellar space was not empty. It was alive with drifting debris, fractured worlds, and chemical seeds. Our galaxy was not a silent void, but a place of constant exchange. And if fragments carrying pre-biotic molecules were traveling freely between star systems, then our own origins might be far more intertwined with the wider cosmos than we ever dared imagine. I thought often about the scar on Venus, the temporary wound carved by a visitor from another sun. It would soon fade, healed by the planet's relentless winds and crushing pressure. But the scientific wound it opened within us would not close so easily. It forced us to confront our vulnerability, our smallness, and yet also our connection to something far larger. We were not isolated, we were immersed. As I reviewed the final summary of the event, I felt a sense of completion, but not closure. The cosmos had spoken, not with words, but with impact and fire. It had torn open the sky of a neighboring world to deliver a message written in atoms and isotopes. And I understood then that the true legacy of 3I/ATLAS would not be the scar it left on Venus, but the one it etched into our understanding of the galaxy. We are not observers at the edge of creation. We are participants in a vast, drifting conversation of matter and memory. And for the first time, we are finally listening.